Afternoon. I'm Yihui Wang from Beijing Jiaotong University. Today I'm going to talk about train rescheduling for urban rail transit systems under disruptions. This presentation includes 5 parts, and first is introduction. This is a map for Beijing metro systems. As we could see here, there are many different lines, and those lines are operated separately. And most of the lines have massive passenger demand. So in order to satisfy the passenger demand, the trains are operated with high operational frequency. So in peak hours, the headway between trains is 2 to 3 minutes. And as we all know that the metro lines have very simple layouts, so the flexibility of the train operation is very low. So when disruption happens, it usually have a very serious effect. However, as we could imagine, disruption is unavoidable. So as this is a data we obtained from 2017. So just in July and August, we could see there are 8 disruptions which lasted longer than 50 minutes that occurred in Beijing metro systems. Some of them happened in peak hours, and some of them happened in off-peak hours. However, as we could see that the disruption in metro systems does not last for like several hours, like 45 hours. In general, they just last for like 20 to 40 minutes. So when disruption happens, the trains are really crowded and there are many passengers on board. So as we could imagine, if a train is blocked in the open track, which is normally tunnel, and it's very dark outside, so the passengers' behavior is uncontrollable. They may break the window and they may jump out from the train. So those are safety issues we need to avoid it. And also, when disruption happens, the capacity of the metro line reduced. So many passengers, they wait inside the station. Of course, when the station reaches to its maximum capacity, then we also introduce some control measures to let the passengers waiting outside. So they need to queue outside the station. So in this case, some of the passengers, they may leave the station. So they may say, I will gonna take the bus, or I will gonna take a taxi. So in this case, many passengers, they just are queuing outside the metro station. They are waiting for the bus or take taxi, and the road networks does not work well. So the best way to solve this problem is effective rescheduling. We want the trains back to normal as soon as possible. The disruption management process in general contains 3 phases. So before the disruption happens, everything works well, and then afterwards, the disruption occurs, and then the transport capacity reduces, and dispatchers, they also make decisions to transfer the state to a stable one. And then when the disruption ends, they will transfer the traffic to normal, to the planned timetable. So this is generally holds for the traditional railway systems, because they will have a stable phase here. They will have a stable phase here, so they will introduce a disruption timetable. However, for metro lines, as we mentioned before, like the whole disruption period is just 20 to 40 minutes. So it's very hard for us to say which is the first phase and which is the second phase. So it's better to consider the whole process for the disruption management. So now let's look at the mathematical formulations. And this is the metro line we considered. It has in total I stations. So among these stations, some of them are just normal stations, which only have 2 platforms and nothing else. And some of the stations, they may have some turnaround facilities, so we call them turnaround stations. Of course, the first station and the last station of this line should be turnaround stations. And also, we will have some turnaround stations be connected with the depots. So in the normal case, the trains are just operated according to the planned timetable. Everything goes well. And however, when the disruption occurs, and then the trains they cannot pass this blockage. It's noted that here we can see the complete blockage. So the trains in both directions cannot pass through. So the trains either they just wait at this station or they need to short turn. Before we formulate the model, we need to make some assumptions. The first one is trains do not meet and overtake each other, and each platform can only accommodate one train at a time. And for the disruptions, we also assume that the trains are not allowed to stop in the open tracks. And to make this hold, we make another assumption is that trains that enter the blockage area before disruption, they can pass through this area. And also for metro lines, we assume that the trains they can arrive earlier or depart earlier if it can back to the normal state as fast as possible. And the disruption we consider here is only happens in off-peak hours. And the metro line is not saturated, because if this disruption happens in peak hours, then the passenger behaviors and the passenger demand we need to consider. So the model will be much more complex. So the objective function in our model we consider is the deviations of the rescheduled timetable with respect to the planned timetable. And also we want to minimize the service cancellations. The service cancellation here also involves the partial cancellations, which is caused by the short turning of trains. If a train short turns and then part of the train services are cancelled. And the third component we want to minimize is the headway variations between the neighboring services. So we want to try to keep stable services, so the headway between trains they don't vary too much. And the constraints we consider here involve those 5 parts. And the first one is the departure and arrival time constraints, which should satisfy the minimum running time constraints and the maximum running time constraints and the minimum waiting time constraints. And if the trains they need to turn around at a station, then it should satisfy the minimum turnaround constraints, and also the headway between the trains they should satisfy the minimum headway. And if a train it turn around at a station, then we also need to make sure that the turnaround train should perform another train services. Otherwise, the rolling stock does not match. For example, if we need extra rolling stocks, they need to come out from the depot, then we need to check if we have available rolling stocks or not. For the solution approach, the formulated problem is a mixed integer nonlinear programming problem. The first step we did is to linearize the problem by using some transformation properties. Afterwards, we can get a mixed integer linear programming problem, which can be solved by existing solvers, such as the Ciplex or Groby. We can use those commercial solvers to solve it. However, the computation time are too long for real-time applications, which could take 10 minutes or may even half an hour to get the optimal solution. So we propose an efficient two-stage approach. So in this two-stage approach, basically what we do is we just reduce the problem size by only consider the important stations where the trains could turn around. So we only consider the short turning possibilities for the trains, and then we could generate a draft train schedule. And then based on this draft train schedule, we use it as an input for the second stage, and then we can get the whole rescheduled timetable. Furthermore, we also introduce some filtering constraints based on the experience of the dispatchers to enhance the computation speed more. And the fourth part is the case study. We tested our model and solution approaches on the Beijing subway line 7, and which has 21 stations. And 11 of them have turnaround facilities. And Beijing, BJX, and JHC are the terminal station. And the depot is connected with SH station here. And for the experiment, we'll assume that the track blockage occurs between stations 6 and 7. And it's a completed blockage. So the intuitive solution would be we hold all the trains at the platform. So this train arrives at this station and the disruption already occurs. So it holds here. And the second train also need to hold at the next station, and third train also. So in this case, we call it the holding strategy. We hold all the trains for this figure here. However, we could hold like 2 trains or 4 trains, and this could be chosen by the dispatchers, or we could set it as a parameter. And this is a train schedule generated by the formulated mathematical model. As we could see there, here they prefer the short turning strategy. So the train arrives here, it cannot pass this area, so it short turns to perform another train services in the opposite direction, and it also holds for the other part. And after the disruption finishes, the train can pass through, and then they can operate the whole train services. And this is a table for the performance comparison between different approaches. And we have the MLP. We also have the two-stage approach, and we have the holding strategy. As we could see that the two-stage approach with filtering constraints, the computation time is less than 1 minute, so which could be satisfy the real-time application constraints. And then the performance of which is also quite good. So it's quite promising. And we also investigate on the effect of the disruption durations. So here the disruption just lasts for 10 minutes, and here is 20 minutes, and here is 30 minutes. As we could see that with the increasing of the duration of the durations, the objective function value also increases. And then the timetable deviations also increases, and the number of the cancellations. And the computation time of the two-stage with filtering constraints in general performs well, but however, for some cases, the computation time is still a little bit long. So now we are arrived at our conclusions. So in this presentation, we look at the train scheduling for completed blockage for metro lines. And in this study, we presented an integrated train rescheduling and rolling stock circulation planning model. And we also try to propose some effective solution approaches to solve the problem. And the generated rescheduled solutions could be used for decision support for dispatchers. Of course, there are many limitations for this research. For example, we could consider other types of disruptions, such as partial blockage and slowly moving trains. And here we assume the disruption occurs at off-peak hours. However, if the disruption occurs during the peak hours, we need to consider the joint optimization of the passenger control strategy and the train rescheduling. That's it. Thank you for your attention. And if you have any questions, please write an email to me. Thank you very much.